Welcome back. And another application of the chain rule arises when we look at parametric curves. And so the idea with a parametric curve is that we've normally studied functions that are functions of x, right? And so we say y is a function of x, meaning that we can write y in terms of x, right? But now we can say that, well, even x depends on a parameter t. So if you can imagine like the x-coordinate changing over time, which causes the y-coordinate to change, that's the sort of scenario that we're in. So we're saying to get x, we have to do something to t, some function of t, and then that in turn means that y is a function of x, which is actually a function of t, so y is actually dependent on t as well. So something a very interesting thing to think about. And when you get into Calc 3, you're going to be doing parametric functions left, right, and sideways, like all the time. Okay, and in fact, you'll do parametric surfaces too, which is really cool. Okay, but when we think about the derivative in these cases where we have a parametric function, we're ultimately applying a time derivative or a derivative with respect to t, and consequently, we're interested in dy dx, right? How y changes in response to changing x, but we have this intermediate variable that we have to go through. And by the chain rule, if this is the case, we would do, dy dx or dy dt, and then we'd have to say that that is equal to dy dx times dx dt. Okay, and that's where this whole thing arises. But if we're interested in dy dx, we can see it is just multiplication because that's what the chain rule is. Next stage of the chain, you have to multiply. So if we divide the dx dt over, we just get that dy dx is dy dt over dx dt. Okay, effectively, if we have equations for for y and t, or y and x in terms of t, take the derivative of y with respect to t over the derivative of x with respect to t. Okay, so for this example here, we have a parametric curve. We can see that we calculate the x and y based on t. And so if we want where the tangent is horizontal or vertical, the tangent has everything to do with the derivative. So if I look at dx dt, derivative of x with respect to time, and keep in mind, we can apply any sort of derivative that we want. We could look at the derivative of x with respect to s, which is something that we don't know, but anything that is not s would differentiate to 0. Regardless, if we differentiate with respect to t, we just have to use the product rule, or the power rule, 6t squared plus 6t minus 12. Okay, and then doing the same thing with y, dy dt is 6t squared plus 6t. Okay, and then if we want where it's horizontal, that would mean that the y component must be 0. So then if I factor this 6t and then t minus 1, or t plus 1, that means that t is equal to 0 and 1 produces a vertical or a horizontal tangent. Okay, but I haven't found the points yet. Okay, these are just the two time values. Okay, for vertical ones, I would need to set dx dt to 0. Okay, divide by 6 to everything, and then factor, I believe you get t plus 2, and then t minus 1. So then solving, t is equal to negative 2 and 1, which is kind of interesting. At t is equal to 1, it would be both vertical and horizontal. And now I see I made a little error. That should be a minus 1, shouldn't it be over there? Okay, so then now it does say find the points. So again, these are t values, so I'm just going to do 0, minus 1, 1, and minus 2, and I still need to find the x and y values. Okay, so then this is as simple as plugging those in, and for time purposes, I'm going to say you can plug them in when you want and get the points. Okay, the overall idea though is present. Okay, and now if we want to find the equations of the tangents to the curve that pass through that, okay, tangents, lines, tangent, that's what we mean here. So then looking at dx dt, and we get just 6t dy dt is 6t squared. Okay, the equation of the tangents, so I have a point, I need to find the tangent slope. So that means I need to find dy dx, which we said above was dy dt over dx dt. So I get 6t squared over 6t, or just t. Okay, and in this case, if I want the value of t, I need to say, well, at some point, I need to make sure that y is equal to 3, but y is also equal to 2t cubed plus 1. And so subtract 1, I get 2 is equal to 2t cubed, and consequently that t is equal to 1. So for this instance, it's just 1. Okay, you could do the same thing with x, and you'll get exactly the same thing, except you'll get plus and minus 1. Okay, so we should check plus and minus 1 as well. But one equation is going to be y minus 3 is equal to 1 times x minus, I have this backwards. Y minus, no, yep, that's right. Y minus 3, x minus 4, like that. And then the other equation, since we found that t was minus 1 from x, we should also report that one. Okay, now that being said, what we should really do is check both of these on the curve. So we should sketch the curve for both of these using Desmos or something and confirm that both of these equations would produce a tangent. That would be the only way to verify that these are both solutions.